Okay, so just a couple of problems here in angular dynamics. First of all, we've done pulley problems for years, but now we can actually include the inertia and friction of the pulley. So first thing to realize is that the force that actually torques the pulley is not the weight in this case. Instead, it's actually tension that torques the pulley. Now, is the tension just the same as the weight? Well, no, it isn't, because if you let this go, this mass is going to accelerate downwards. And as a result, the tension will have to be different from the weight. So tension torques the pulley. That's the first thing to realize. It's tension acting a distance r from the center that creates the torque. The other thing to realize is that since the net force on this mass is mg minus tension, that the tension is actually less than the weight of that hanging mass. So to say that the torque on this pulley was mg times r would be overestimating the torque. Now, if you include the inertia of the pulley, then something else happens that's interesting. If we consider the dynamics of the pulley, we see there's two forces on it, the two string tensions, which both torque the pulley. Now, those two tensions, if you ignore the mass of the pulley, then they're just the same. That's what we've always assumed before, right? That those two tensions are the same, and they will be for a massless pulley, okay? But if you include the inertia of the pulley, if we consider a net torque equation on the pulley, then, okay, clearly note that this mass is greater, so we expect this to fall. That means that the pulley, we expect it to accelerate in this way. In order to have an acceleration, you must have a net torque. And the net torque, as we said earlier, is going to come from the tensions. So there's a tension 1 torque and a tension 2 torque, which are opposite to each other. So the net torque in this case is going to be the counterclockwise, subtract the clockwise. The counterclockwise is due to force T1. A torque is a force times a distance. The distance from the pivot point, or the axis of rotation, is just the radius of the pulley, r. Now the clockwise torque comes from that second string. I'm using T for tension in this case. It's opposite, so we subtract. And that will equal I alpha. Now, if the pulley has no mass, then it has no inertia. This side's 0, and the two tensions are equal. But if the pulley does have mass, then it must be that T1 is greater. So for a pulley with mass, the two tensions are not equal to each other, and T1 will be greater. And this is the problem of interest to us here. So, two ideas to keep in mind with these problems. Tension torques the pulley, and the two tensions aren't the same. The one that's winning in the direction of the acceleration must be larger. So let's try a problem then. Here it is. Well, it's kind of the one we were just looking at. We'll start by drawing the forces just on the masses. Now, this is something we've done many times before. We know there's a weight force on this side and a tension. This one's got a weight force on it and a tension. Now, we've just said those two tensions won't be the same because the pulley has mass. The pulley's got inertia here. So if we label these forces, let's call this tension 1, this one tension 2. This is mg, or 2 g's of weight. This is mg, or 1 g of weight. This one's going to go down. This one's going to go up with exactly the same acceleration. So if we write our force equations, net force will equal ma. The net force on this mass, because the acceleration's down, the net force is down. So 2g has got to be bigger than tension 1. So we take the bigger force and subtract the smaller force and set it equal to ma. The mass is 2 kilograms. On this mass, the acceleration's up, so the net force has to be up. So tension 2 has to be bigger than the weight. So the net force is tension 2 minus the weight is ma, which mass? That's 1 kilogram. Now, in our previous physics courses, these two tensions are the same, and we would be done. But when we include the inertia of the pulley, they're not the same, and now we have 3 unknowns, and so we can't solve that system yet. What we need to do is consider the forces acting on the pulley, and I'm just going to redraw it over here for that force analysis. We're going to write equations for the rotational dynamics of the pulley. So we've got tension T1 on this side. Because this weight's larger, that tension T1 will be a little bit bigger than the tension T2. We've also got an upwards force that is supporting the pulley in this string right here, and we've also got weight of the pulley. Now, the pulley, whatever it's doing, isn't going up or down, it's just rotating. So as a result, these forces have to be balanced. So this is the T1 force, this is the T2 force, and this is the weight mg, so 2.5 g. So on the pulley, the sum of the forces must be 0 because it doesn't go up or down. So that's F minus T1 minus T2 minus 2.5 g's. Now, in terms of the rotational dynamics for the torque, then, like we said before, there's an angular acceleration in the anti-clockwise direction here. So the tension 1 torque has to win. And this torque is due to T1. So as we wrote on the other page, the torque will be T1 times r, the radius of the pulley. And the radius is given here. The clockwise torque comes from tension T2. These two forces act at the pivot and don't produce any torque, so they're not in the torque equation. Now, a couple of things here. We will treat all pulleys as disks. So the inertia of a disk is 1/2 times the mass of the pulley times its radius squared. If the string does not slip on the pulley wheel, then there's a relationship between the angular acceleration alpha and the acceleration of the string a. A will equal r alpha, or alpha will equal a over r, where that acceleration equals the acceleration of the string and therefore equals the acceleration of the two masses. So putting that all together, you get this for, that's equals, believe it or not, you get this for your net torque equation. Now clearly there's some algebra we can do there, and we should now be able to solve the system. So how do we go about solving that system? Well, here the equations are all recopied for us. I prefer to do it by elimination. I notice that one of the r's cancels here, and then I can factor an r out on this side. And that'll cancel the one remaining r. So I now get T1 minus T2 is 1/2 ma. M is just the mass of the pulley. So I get this expression for T1 minus T2. I'm going to write it over here. Now 1/2 of 2.5 is 1.25. And I now see that if I add those three equations together, that minus T1 plus T1 cancels, plus T2 minus T2 cancels, and I just get 2g minus 1g is 2 plus 1 plus 1.25 a. I can solve for the acceleration. It's just g over 4.25. So it's about 2 meters per second squared, a bit more than 2. 9.8 over 4.25. Let's see what that is. So it's 2.30 meters per second squared. Okay, so that's how the analysis works. And there's some concepts in there, right? You need to realize that tension torques the pulley, that the tensions aren't the same as each other, and they're not the same as the weight. You need to write the net force equations for the masses, like we did before, and then write a net torque equation for the pulley. The torque on a pulley will be the tension force acting a distance r away. So here's one in the homework section for you to try. The answer is given. Make sure you can work that one out. So this is one problem in rotational dynamics that we won't have time for in class. I just want to expose you to it. Here's another one, rolling down the ramp. Now, with rolling, a rolling object, it actually takes friction to make an object roll. Because if you consider the forces on an object, this turns out to be a disk, well, there'll be a gravitational force, there'll be a normal force. Both of those, you'll notice, act through the center of mass. Neither of those create any torque. So if those are the only two forces that act on the object, it just slides down the ramp and it doesn't rotate. What actually makes objects rotate when they're rolling is a friction force. Now, as we said earlier, when it's rolling, this point's in contact with the ground. So that means it's actually not a sliding kinetic friction force, and you're not actually creating heat energy there. It's actually a force of static friction. So there's a static friction force here. This is the good old normal force, and this is the mg force. So that's the force diagram for a rolling object. Now, we will, as we always do, resolve gravity into components. The angle of the component triangle here is always the same as the ramp angle, theta. And gravity is squeezing us onto the ramp and pulling us down the ramp. So this is the familiar mg cos theta component. This is the familiar mg sine theta component. So now we're going to write force and torque equations. So sum of the forces, and let's use this as our coordinate system. Y is always perpendicular to the ramp, x is parallel. So the sum of the y forces, we've got normal force, and we've got mg cos theta opposite. Those sum to 0 because there's no motion in the y direction. In the x direction, it accelerates down the ramp, so there's an unbalanced force, mg sine theta minus friction equals ma. Now, in our previous life, we would have been given a value for mu. You'd find normal force, stub it in there, find friction, because of course friction equals mu Fn, but we don't know what mu is, so we can't currently solve this system. So the way to proceed is to analyze the rotational motion of this object, because if it's accelerating and rolling, if it's rolling, rather spinning, we should be able to find something out by applying Newton's second law for rotation. Okay, now the torques. Well, we said before that the normal force and gravity, the weight, don't create any torque because they both act through the center of mass. So the torque is just due to the friction force. Now, a torque, of course, is a force times a distance. Force times distance. The force is the friction force. The distance, if we're taking torques about the center of mass, is just the radius r. So there's the friction torque. That's got to equal I alpha. Now, we were told that this is a disk, and the inertia of a disk is 1/2 mr squared. It's rolling. Rolling means it's not slipping. And as we saw in the previous problem, that means the angular acceleration is equal to a over r. Now we can cancel one r, cancel the second r. That simplifies to be friction is 1/2 ma, where m is actually the mass of the object. So now friction's been related to the acceleration. We can just substitute that back in. And so if we put those two things together, we had mg sine theta minus friction, I'll use this value for friction, equals ma. Now we'll bring the 1/2 ma over and add it to ma, and that'll give us 3/2 ma. And then that equals mg sine of theta. Cross-multiplying the 2/3 and canceling the m, we get an acceleration for rolling down the ramp of 2/3 g sine theta. Now, if there was no friction, it would just slide down the ramp, and the acceleration would be g sine theta. So we've obviously got a little bit less acceleration because of the presence of friction. But if there was no friction, then there wouldn't be any rotation. So it turns out that with rolling, we end up with just as much energy, considering the translation and the rotation. We end up with just as much energy as we started with. and just as much energy as you would if it was actually not rotating, if it was just sliding down a frictionless surface. So the static friction gives us this rotational acceleration alpha that's a little bit less than the frictionless case. Here's one for you to try next. Now, analyze the dynamics of a rolling hoop. We just did a rolling disk. And show that you get these conclusions for the hoop. These are the conclusions. This is what we just found for the acceleration. For comparison purposes, you can work out the corresponding angular acceleration and friction. And then these are the equations for the hoop. So try and show that. And that's a bit of theory and a couple of problems for you to do related to angular dynamics.